Okay, Assalamu alaikum. For those who just joined in, few announcements. One is that I posted when the midterm is going to be, and also I posted the project information. Please read all project documents carefully, very well, and be careful about the deadlines that's set there. And please do not communicate with me the deadlines anymore. You already have them there. Don't ask me in an email or in the class when is the deadline. Please go and read the document to see the deadline. Reason for that, I have other projects for other classes. I might mix the date and give you a wrong date. Still, you are responsible. So what govern the um, things between me and you is that document. So please read it well, and this will tell me that you have read it. Okay. If you ask me when is the deadline, I know that you did not read. Okay. So with no further delay, uh, okay, be quick because we have a lot of material to cover here. Said. Okay, let's take that maybe offline so we don't delay all the class. So if you can, I have office hours right after the class. So you can see me in Team Center. Okay, MS Teams, not Team Center. Okay, well, so this is where we stopped last time, talking about the nature of ethics problem. Okay, and the ethical problem are often open-ended. There is more than one solution for correct solution for that problem. It is, by the way, very, very similar to the design problem. Okay, that's why they use some analogy later on in problem solving technique that is used for design to be used for ethical problem. There will typically be a range of possible solution to the ethical problem. Driving a good solution requires analytical skill that draw from the large body of knowledge. So as you read more about the cases that are already discussed and resolved, that will build your intuition on how to address the problems there. Okay. Pitfalls. And by pitfalls, we mean that what do you call it? Traps that you could fall in and violate the ethical code there. One of the pitfalls is that when you are looking at a problem, you search for a single cause. Okay, so you are searching for only one cause that caused this problem to happen. Okay, you need to explore all other possibilities, not only one single cause. Subjectivity versus objectivity. Okay, so objectivity, you are data driven. Subjectivity, it means that I feel, okay, this is what happened. That's not a way to think about the causes. Okay, you need to be objective, not subjective. To search to affix blame, and this is one of the biggest pitfalls there. When an ethical issue occur and it is hot, okay, people try to blame somebody there to close the case and finish it. Okay, so don't fall in that pitfall. Rush to legalism, and this is another issue that people also haste when they see some ethical issue. They try to put rules to stop this from happening again. Okay, and by putting so many legislations that deprive the engineering work to be creative. Okay, no need for rules if things can be worked around with the ethical solution. The loose attribution of the phrase which says it's just human error. Okay, so trying to evade the problem by saying that it's a human error. Okay, or a fixation on the technical failures. So trying to make a cosmetic fix to the symptoms rather than go deep into the technical problem solution. And this is common in fires, okay, or building collapse. When there is a fire, trying to do a fixation there, and that causes the fire to occur. Others, okay, ethics test. So there is ways that you can, in general, test the ethics problem to see that do I have an ethical issue with that problem or that decision or no. Okay, number one is looking into the harm and beneficence. Beneficence is the good, okay, and harm, we know, is the bad thing happened to you. So you ask yourself, does it do less harm and more good than the other alternatives? So my decision here or my choice here, does it do less harm and more good compared to the other alternatives? And this test is about the alternatives for all stakeholders. And the word stakeholders here, we mean that all people that have something to do with that decision. Okay. Sometimes the stakeholders are the public, who are the users of that product. Okay, so we need to put into account or have in our mind all the stakeholders, not to miss any, because that could be the issue or the ethical issue that we are missing. Publicity, that's the second test. Would I want this choice published in the newspaper? Okay, sometimes when you make a choice that you're not comfortable with, of course, you don't want that to be announced in the or published in the newspaper, because it will backfire on you. Okay, so this is test is about what decision would show about your character. Okay, reversibility. That's the third test. Would I think this a good choice if I were among those who are affected by it? So you're putting yourself in the stakeholders' shoes, okay? And this choice is about whether stakeholders are being treated with respect or no, okay? Other tests, code of ethics. How does this choice relate to the ethical standards of my profession? So then I have to compare this choice that I made. Is it in line with the standard ethical codes in my profession? And this is a test about the decision maker duties in his or her role as a professional. There is a term there used in the ethical quotes that did I exercise what is known as the standard of care. Okay, and this is where you draw the line that this guy was his work was a negligence, or it was a good engineering work, but things did go wrong. Okay, feasibility. Can this solution be implemented? And also, this is when we give feasibility study. Okay, we have to keep in mind these things. So can this solution be implemented given time? Okay, the time that's available to you. Technical. So do I have the technical how to do it? Economic, legal, and social consideration. All this has to be in mind when you give feasibility studies. Because if you overlook any of these, it will bite you later, and that could be a source of ethical issues there. So this test is about practicing issues, and this might be a big pitfall here, source for pitfall, if you don't treat this one equally. Okay. Conclusions of this introduction part. Engineering is our profession, so it is not just a job. Okay, so by profession we mean that we have obligations towards all stakeholders there. Study of engineering ethics can guide us in resolving the moral dilemmas we might encounter. Okay, so by learning engineering ethics, so it gives us or open our eyes and shed the light when we are conflicted with some moral dilemmas at work as professionals. Being responsible is what a professional is all about. Okay, so you took this status, which is securing for you high pay, okay, only because you are responsible individual. Okay, our goal must be to become morally autonomous, and I talked about this term before. By that we mean we said you have naqd dhati. Okay, so you are critical and independent when you are dealing with duties that professional duties. Okay, we will look at some quick questions, practice questions. So here says choose the most appropriate answer. Okay, ethics can be defined as the study of the characteristics of morals, the study of the moral choices made by every person in his or her relationship with the other persons. Number C, A and B is the correct answer. And number D says none of the above is the correct answer. Okay, so can you put to me what is your answer section? Okay, good. So if your answer is C, yes, that's the correct answer. Okay, because A and B combined together will give you a definition of what is the ethics. Okay. Ethical problems in engineering often have unique solution, multiple disjoint, no overlap solutions, multiple and sometimes conflicting solutions, sometimes no solutions at all. Okay, good. I hear, I don't see your answers so far, but if your answer is C, okay, that's the right choice there. Okay, professional ethics deal with how we treat others in our day-to-day lives. Okay, involve choices regarding relationship between organizations and individuals. Involve choices regarding a relationship between organizations, government, and individuals. None of the above. Okay. Again, if your answer is C, that's the correct choice. Okay.
Doctor.
Yes.
What's the difference between B and C?
You figure it out. By the way, this is the assessment is going to be this way, right? Between B and C, there is the government part, which is missing in B, right? And if you go to the definition that we give in the slide, it involves the government, organizations to organizations, and governments to individuals. Okay? All right, so now we're going to switch to the next topic, which is, I think from my side, is an interesting topic. Okay, we'll see how that will interest you there. Okay, we're going to take now one case study and explore it. Okay, and we're going to talk about the Challenger disaster. And the Challenger is a spaceship, okay, that used to be sent to the space. And we will look into what is the issue with that spaceship. Okay. Tentative lecture schedule. So we are in week 3 and we're studying the Challenger disaster. That's we're doing good, but we need to wrap it up today. I want to just to pay attention to the midterm date, Tuesday, October 20, from 5 to 6, maybe 5 to 5:50, but we'll cover the whole period, so we'll be protected in that time. Well, there is a small movie here, and there is many, I think, movies that related to this disasters in YouTube. You can watch at your own time. Okay, I'm going to go ahead into the details of the case. And usually, when you start your ethical problem, you need to understand, for example, the technical part of the problem first. Okay, and then look at the other sides of the problem. So we're going to look at it into in the technical part, and then go ahead and look at the political part and management and stuff like that. Okay, so the Challenger is made up of many parts. Okay, it's not one piece spaceship. Okay, and there is a reason for that. There is an engineering reason for that. So the space shuttle. Okay, one other thing I want to just clarify to the others who are not mechanical engineering maybe background. Okay, don't worry about the technical details. Try to grasp as much as you can. Okay, and since you are from an engineering background, what went wrong, you can understand that technically, but not necessarily you know everything there. Okay, so the spaceship is made up of three main parts. The orbiter, which is in the picture, looks like an airplane here. This is the orbiter. Okay, and it is a huge glider, and by glider we mean that airplanes that fly without engine. You will tell me, well, I can see 3 engines there in that one. Yes, that's correct. But when it re-enters back the atmosphere of air, of Earth, then it will glide. It will not have an engine turned on at that point. Okay, so that's why they call it glider. External tank, and this is the brown piece here, and that is filled with fluid fuel. Okay, oxygen and hydrogen fuel for the shuttle engines. So shuttle engines, those 3 shuttle engines are fueled from this tank, which is known as the external tank. Okay, and then there is 2 solid rocket boosters, this one on the right and this one on the left there. And this has solid fuel on them. Okay, and they are just like the firecrackers that you use when celebrating an event. Okay, so they are similar to those firecrackers, but they are bigger and more controlled in that sense. Okay. Other technical information. Most complex machines ever built, this one is the most complex machine that human made. And this is show from the 2.5 million parts that it is made of. So we're talking about 2.5 million parts that this spaceship is made of. It has 230 miles of wiring. That's about 370 kilometers of wiring there. It has 1,000 valves, over 1,400 circuit breakers, and over 27,000 thermal tiles. Thermal tiles are used to be put on the body of the orbiter to protect it from the high temperature when it enters the atmosphere again, re-enter the atmosphere. Okay, there are 16,000 people help prepare the shuttle for launch. Okay, over 1.3 million separate jobs are performed to prepare the shuttle for launch. It takes about 3 to 4 months of constant work to prepare an orbiter for launch. I forgot to mention that it is made of 3 main pieces there, because NASA convinced the Congress that they're going to build a reusable spaceship, okay, that can be sent to the space many times during the year, okay, and that's why they have this external tank, and they have these booster rockets. So and the main orbiter can be reused. So both the booster rockets and the main orbiter can be used. The only consumable one is the AT, which is the external fuel tank. Okay. So that's why it takes 3 to 4 months of constant work to prepare the orbiter for launch. Each shuttle mission costs about $500 million. This is, of course, for the solid rockets and the external fuel tank. And of course, even the ship itself needs some consumables there. But the orbiter itself, which is the spaceship, costs about $2 billion. And this takes about 5 years to build. Okay. The shuttle weighs 4.5 million pounds. Okay. At liftoff, over 3.5 million pounds of this weight is fuel. So you can see now that you're using a fuel which is 3.5 million pounds to lift up 1 million pounds shuttle. Okay. And this fuel will be used up or consumed in about 8.5 minutes ride to the orbit. Okay. At launch, the shuttle solid rockets, booster rockets, burned more than 10 tons of fuel per second. Okay, and produce, and this is the biggest thing, by the way, when we took the introduction to mechanical engineering, we talked about the Apollo at that time, and we said this is one of the top 10 achievements of mechanical engineers, that they produce 44 million horsepower to be able to lift that spaceship. So this is a very huge horsepower, and that will be for about a period or a duration of only 2 minutes of the flight. At takeoff, all engines are operating. So the 3 main engines on the shuttle are receiving liquid fuel from the external tank. The solid fuel in the 2 solid rocket boosters is lit. They put 10 lit those rockets, similar to when you lit the or light the firecracker. So altogether, the shuttle engines produce about 7.3 million pounds of thrust. Thrust is a push force that push the spaceship up. Okay. So after takeoff, okay, 2 minutes after takeoff, the solid rocket boosters separate and parachute down into the ocean. So those 2 solid rocket boosters, they finish their job, they consume all the fuel that they have, so then they separate from the spaceship, and then they parachute to the ocean. They will be recovered and reused for future flights. Okay, so they are not disposable ones. The ET, which is the external tank, is dumped once the orbiter reaches the orbit. So it will be using all the fuel, okay, until it reaches the orbit. Then after that, it will be dumped. So it will be falling, and when it enters the atmosphere, it will be all burned up. And you can see how much technical work that is put there. So selection of the material of the ET and stuff like that. So it will be burned completely when it enter the atmosphere without causing any environmental issue, or a debris of it does not burn and it come and hit somebody on Earth. Okay. So we can see big responsibilities for engineers there. So the only non-consumable part is the ET. Okay. Now we're going to talk, that was technical things about the Challenger itself in general. Now we're going to talk about the incident there. So the Challenger disaster on the 28th of January 1986. And you will see that ethics problems always have dates and times and stuff like that, because when they did the investigation, In the report, these things are important. So they have this information recorded. So the Challenger shuttle exploded exactly about 80 seconds after liftoff. So 80 seconds after liftoff means that boosters are still having some fuel in them, booster rockets. Okay. So after lengthy and detailed investigation, it was determined that the cause was the right solid rocket booster there. Okay, that was the issue, which is now you can see with the arrow pointed to in the picture there. Okay, the solid rocket booster are manufactured by a company called Morton Thiokol. Okay, this is a supplier to the NASA. The solid rockets use solid fuel and do not have an actual engine in them. So there is no valves, no pipes, no pumps, stuff like that. Okay. So they are like a huge, as I said before, firecrackers. And they are lit and kept burning until the fuel is gone. So we can see here a big disadvantage here of those solid rocket boosters, that when you light them, okay, that's it. You cannot turn it off. Okay, not like the liquid fuel engines. You can turn off the ignition and then you can stop it from burning anymore. Those, when you lit them, that's it. They will go until they burn all the fuel. After that, then they will stop progressing. Okay. All right. Okay. So what we were saying. Okay. So they are about 149 feet, about 50 meters long, and made of 4 main sections that are connected together to make the booster. Okay. The sections are filled with the solid rocket fuel at the company's plant in Utah, then shipped to Kennedy Space Center in Florida, where they are assembled. Okay, so it is made of 4 parts because putting it together as one part and then try to ship it will be a challenge. So they make it out of 4 parts, which can be assembled there in the spaceship Space Center, Kennedy Space Center. Okay. Now, these RSPs, okay, sections will be connected to each other, okay, and I need to maybe open this more, and we can see them here in the picture on the right here. Okay, so the 4 fuel segments is this 1, 2, 3, and 4. Okay, here we have the nozzle cap, we have the parachute, it's put here, and then we have here computers, okay, which controls the thing here. And then we have the pieces. Between them there is O-rings, and we will see what is the O-ring does there. And we know O-rings in general are made of rubber material, okay. And then we have here the nozzle, okay, and the aft skirt and other pieces. So how these 2 parts are connected is using what is known as a tang and clevis joint, okay. And the tank and clevis joint is this what we see here. So this part, okay, belong to the lower one. So all this piece here, okay, belong to the lower segment. So this will be the thickness of the segment. So if you will, this is an axisymmetric view or axisymmetry. Axisymmetric view means that if I revolve this about the center, I'm going to get the cylindrical shape that I need. And this tang, okay, is belonging to the upper one. Okay, so this is how the what do you call it? The two pieces are connected together, and then the tang is attached to the clevis here by a pin. Okay, and this pin here, they have about 177 pin all over the circumference of this thing. Okay, I spent time here because the issue that we're encounter in this joint here. Here we have two views of the joint. This is normal joint without any issue, and this is the joint when gases heat up due to the burning fuel inside, and then expands these tanks. Okay, then what happened? You can see here the tank here of the upper is rotating, and they call it here in a phenomena known as rotating joint or joint rotation. Okay, the job of the O-rings here is supposedly that this putty here is an insulator material, okay, which is going to push this part of the clevis against the tank, and then these O-rings will seal the hot air, because we said this, when you revolve it, you will have the cylinder, so hot air will be coming inside because of the burning of the solid fuel. So it will try to escape outside, right? So this is these O-rings to make sure that no air will escape. Okay, so I hope that you understood the joint, and this is another picture of it. We're going to go into more details on it. So to make sure that the hot gas does not escape from the joint, two rubber O-rings are placed in the joint. Okay, and in a former model of this rocket, which was used for other purposes, they use only one O-ring, and they made this modification for the shuttle to make sure that no issue will happen. So they added another O-ring to protect there. Okay, since rubber may burn if exposed to the hot gases, okay, then they put the putty, which is this material here, in the I don't know what is this color, magenta or something like that. So it is the H one. Okay. Then let's go through the other parts. This is again our tank A, okay, which is the steel wall of the upper container, and B is the ferrous O-ring, and C is the second O-ring. Okay, and then a strengthening band here for D to make sure the joint is strong enough. Okay, and then we have the E is an insulation, F also is an insulation here, two layers of insulations, and then we have a carpeting layer, and then we have the fuel, which is the gray area here, and we have the sealing paste, which is the putty that they're talking about there. Okay, and we can see here a close picture of what happened at the start of the launch. So we can see black smoke is coming out of this area, and you can see here how it opened a little bit here, the connector. Okay, so as the problem we had, as the solid fuel start to burn inside the different sections, the metal skin expand. This cause what is known as a joint rotation. The tank of the upper section tilts within the clavus. We saw the picture of the lower joint, leaving a gap that would allow the hot gas to reach the O-rings. Okay, so that gap opening will allow the hot gas to come and then touch the O-rings. And of course, when it does that, then it burns it or it will erode the gases. Yeah, can you hear me now? Well, still lagging? Okay, how about now? How about now? Still lagging? Metal skin will expand, and then the tongue of the upper tank will be tilted in the clavus joint as we saw in the picture before, as we show here. So it is tilted in this picture. Then it will, as it tilted in the picture, then it will allow the air to escape. Okay, so now hot air from inside will be escaping through this opening and then heat up these O-rings. So it can erode it or burn it. Okay. Okay. So let me go back. So this was first documented in 1977, and then several solutions were tried to fix the problem. So the engineers tried to do correction to that. So this is a history that when they investigate, we're able to dig out documents that says this issue was seen in 1977. After a flight in January 1985, Thiokol discovered during their routine post-flight check, because as we said, those boosters are recovered from the ocean and reused. So when they looked at them and to check, okay, they found some oil on the outside of one of the SRBs. Okay, What does that mean? It means that hot gases were escaping past the O-rings. Okay, but at that point, of course, no issue was happening because the rocket did its job to the spaceship, and then it parted from the spaceship and came back. So more analysis indicated that the temperature during that flight was 53 Fahrenheit, so about 12 Celsius. Okay, so it is below freezing. Okay, so they conducted that, concluded that probably the rubber material, which is the O-ring material, lost its flexibility. It became less resilience, okay, as it's supposed to be. So then it failed to fill in the gap there. Okay. The shuttle Challenger was scheduled for flight in early January 1986, so the beginning of the month of January. So before the flight, cold weather was expected in Florida. So they looked at the forecast, and they learned that there is a cold front is coming. So therefore, the flight was delayed until the 28th of January. Okay, to escape that period of the cold front. The cold weather did not reach Florida in early January. So that forecast did not happen. Instead of it is coming at the early, it come around the January 28th, 26, which is about 2 days to the new date of launch. So the weather was expected to reach a low of 30 Fahrenheit. Remember, in the previous we said the issue that they have seen at temperature of 53 Fahrenheit. So this is to give you the politics behind the issue there. We know now the technical issue. Okay, now we want to look at the politics behind that. So the budget of NASA is set by the Congress. So Congress give NASA the money to use for spaceship programs. NASA had claimed that the shuttle would be able to go to space whenever needed. So by building it the way we described before, that it will be ready to go whenever is needed. Carry whatever needed and do it repeatedly within minimal cost, which is the $500 million. Okay, so until now, 1985, NASA had not been able to deliver on this claim. So when they claim this to get money from the Congress, okay, but after that, when they made the ship, they never were able to launch on time. So they were afraid that the Congress threatened them about that. You claimed you need that money to be able to send this ship whenever is needed with the minimal cost and all these claims. Okay, so we can see how politics are heating up. President Ronald Reagan was going to deliver his State of the Union address, and this is a yearly meeting that or addressing of the public that he tells what's the things that are done by his government during the year. Okay, and he wanted to mention this Challenger flight, and there was a big propaganda behind it because there was a work between NASA and the Ministry of Education about space awareness in education, and they decided to take a guest astronaut, a teacher in that flight. So that's why there was a big media covering for that to cover this part. And Reagan wanted to announce that in his talk. Okay. Also, Vice President George Bush, that's the old guy, okay, was a vice president for Reagan, planned to attend this launch. And when it was first delayed, and rescheduled. Then he made his schedule to attend the second one, and they didn't want to come short of that. Okay. So for them, it is impossible to change the time to affect his schedule. So he was NASA biggest supporter in the Reagan administration, so they don't want to lose his support there. So that's the politics behind the issue there. Okay, we have few slides to cover, and we are out of the time. So anyway, I will let you read the rest, and I will come later next class, go over them quickly there. Okay, if you allow me to go for more about 5 minutes, we can finish this part, because the coming part is a longer one. So let me hear your comments. Okay, so how about I will continue for 5 minutes plus, and if you have to go, please do so. I'm already satisfied with the attendance, but please come and watch this 5 minutes that will be recorded for you. Okay. All right. So we continue on that. So then NASA checked with all companies to get the okay for launch in cold weather. So everyone agreed. So they have to consult their suppliers, make sure that their parts or their components will function properly when they are under cold weather. Okay. The night before the launch, a meeting was held with THEOCOL engineers and management and NASA management. So these are the management in NASA that are responsible for the booster rocket there, met with the engineers from THEOCOL and their management. Okay, to discuss the issue of the performance of the SRBs in the cold weather. THEOCOL engineers said that the launch should be delayed. And this is a guy known by Roger Boisjoli, and this is the key guy in this ethical issue. Okay, the lowest temperature in which the shuttle was launched before was 53 degrees, as we learned before. And there was a gas escape from the O-ring. Okay. The vice president for engineering at THEOCOL recommended a delay until the temperature would be at least above 53. Okay. The manager of the SRB project at NASA, because now this guy will be the manager who is responsible for delaying the shuttle. Okay, so that's why he is in the hot seat. Okay, said there was not enough data to support the connection between temperature and the escape of the gas. So he said that there is no conclusive engineering evidence, okay, that there is a relationship between the temperature and the escape of the gas. So he's trying to say that maybe the escape of the gas is coming from something else. And even if that happened, then he should question why did it escape, right? This to tell you when management under hot seat or sitting on the hot seat, they don't think straight. Okay, he recommended a go ahead with the launch. The senior manager at THEOCOL asked the vice president for engineering to take off his engineers' hat and put on his management hat. And this became a phrase that is used in the ethics field a lot. Okay, so while they are talking in the teleconference meeting, then the senior manager at THECOL asked NASA that they will be discussing things offline together, and then they will come back. So when they talked to the engineering manager there, he told him that take your engineering hat off and put on your management hat, saying that we're going to lose big business if we delay this launch with NASA. Okay, so what happened that the vice president for engineering now changed his recommendation to go ahead. Okay, and the reason for that, he said he could not see a clear direct connection between the temperature and the gas escape. Okay, so this tells you when you cave in under pressure as an engineer. This is not a manager, a purely manager. He is an engineering manager and knows exactly what is the issue there. So the launch of the Mission 25 took place in the coldest weather ever for a launch 36 degrees Fahrenheit. In some other literature, that temperature at the joint, at the rubber, was measured to be 28 Fahrenheit. Okay, so the cold temperature caused the rubber O-ring to fail in the lower joint of the Challenger right SRB. And at liftoff, black smoke shot out from the joint, indicating that the O-ring were burned up. So they're burned up, it means it is open now for the hot air to come out. So what happened that at time 59 seconds, okay, a fire flame starts shooting off, and the rocket booster rocket joint is broke, okay, or affected. Then what happened? The booster rocket swung. Swung means that it moved away from the fuel tank, external fuel tank, and then it punched in the fuel tank. So then the fire that was coming out of the booster rocket started to burn on the external fuel tank. And of course, since it's coming from outside, then whatever controls that the astronauts have on this external tank to shut off the engines will not work. And in time of seconds, this external tank blew up, burning the spaceship with it. Yes, what happened that the what do you call it? The astronauts, okay, what do you call it? The cockpit of those astronauts split off the shuttle, and then it came down to the ocean, but it slammed at the ocean at 200 miles per hour, which was a big impact there, and that impact caused all 7 astronauts to die. Of course, those astronauts have some connection with the Earth that they will check on their what do you call it, vitals, to make sure that they are healthy. And the scientists noticed that they were alive until this point of impact, and after that, all 7 died. Okay, so we can see what a big disaster when you overlook small things like that. It can bite you up. So the engineer, so the manager in NASA counted on the odds there. Okay, so he said we flew several times, no issue happened. So why would it happen now? That's I'm just reading what is happening in his mind. So instead of saying that I am the one who delayed the launch and then be blamed for that and maybe lose his job for that reason. Okay. Of course, this is not the end of the investigation. There was a big investigation, and then come out of that investigation that NASA administration has to be reformed, meaning that the management has to be reformed to change this culture of trying to cover things and be able to escape there. Okay, I think that's it for today. So if those who are in, if you have questions, please post it. If not, we will close with this talk. Okay, guys, thank you very much, and see you next week, inshallah. Assalamu alaikum.